think this shows you with which kind of machines we are dealing at John Deere. It's not only the big tractors, we also produce a lot of lawn and garden equipment and other items. I will give you in this agenda a little bit about the history, what we are doing in numerical simulation at John Deere, experimental simulation. I also say experimental stimulation because I will come later words to this, and compare these two items in physics, if these are competitors or partners, and give you a conclusion. A little bit of John Deere. We are one of the companies who are very old. You see, 1837, John Deere was founded, and another company in Germany, it was Lanz, in 1859, and they came together in the 50s of the last millennium to join John Deere worldwide. And you see, at the moment, we have 65 factories in 19 countries and more or less 67,000 employees worldwide. To give you an impression, the size of the company and what's behind when I talk about simulation and testing. John Deere, this is the 2013 numbers. The 14 numbers are looking not as good because the industry is down in the agricultural business because we have such kind of a cycle of 7 years or 10 years. But with 38 billion, I would say, of income and 3.5 billion of profit or revenue, it's something which John Deere can be proud of. Another item which is very important, John Deere is investing a lot in the future. The innovation through investment is clear, defined. We invest 3.3% of our income for capital investments, which also relates to maybe experimental testing. We invest 4.2% of our income to research and development, and you see more or less $5 million per day we invest in the future. In Region 2, this is Europe and close by Russia and other countries, we have 12 factories, 12,000 employees, and we also have a marketing unit and sales unit here in Italy, and one technology center in Germany. Germany, we have 6 locations and 7,500 employees, and we do with 3.3 billion of turnover, 40% of the German agricultural engineering industry. And this is Mannheim, and I show you where all the development and the testing and simulation is done. These are here the buildings, and I come later to it. You do not need so many buildings for people. You need also a lot of buildings for doing testing. In Mannheim, we already produced 1.6 million tractors since 1921, and we produce 2/3 of the German tractor industry. But all the things are going outside Germany, they're going to the world, and the things. Now come to the real world. What we do is numerical simulation. You see here, this is a frame of a John Deere tractor, which is produced in Mannheim and all over the world. And you see here, it's some kind of a bending and torsion mode, which is applied here. And you see here the stresses. So we do structural analysis and optimization in this area. On the other side, here you see heat transfer and other things. This is a tractor in a wind tunnel. And this wind tunnel we have also on the experimental side. And why we need a wind tunnel? A tractor is different to a truck or a car. A car is cooled by the airstream which is coming in during driving. The tractor is just different. A tractor uses his whole power when he is driving maybe 3, 4, 5 kilometers per hour in the field. And so you have a different kind of, I would say, a problem to get rid of the air, of the heat which is coming out of the engine. And the worst thing is when you have a backwind and you get the hot wind again in your cooling system. So we're doing also something here for the guy in the cab. The cab at the moment, it's not like in the tractor 20 years ago. It's a very sophisticated thing with a sound system, with an air conditioning system. And it's very important because this poor guy is sitting in the greenhouse and the sun is shining in and you need a lot of cooling capacity. So we're doing some kind of simulation to get the right airstream to the guy. And there are also difficulties to compare it with the people who are sitting in, because in America, in the States, the people want to have the cold stream in the air, in the face, and in Europe, nobody wants it direct in the face. In another area, we do vehicle dynamics. You see here a tractor. A tractor is like a Swiss Army knife without some kind of implements or other parts in the back or in the front. You can do only going into church on Sunday. You see here, this is a model of a round baler. When you going and going through a street and you want to have to get around some kind of obstacles, you can drop the baler on the side. And so we do also this kind of vehicle dynamics things. And we do model-based design, software in the loop, hardware in the loop, whole drivetrain with all kind of components for shifting. We shift in 10 milliseconds. And this is very important that you do simulation up front. And here it's the newest thing when you look to Volkswagen, they have trouble with the emissions. This is one part of the emission system to put in here some kind of special fluid to get rid of the NH. You see more things. We do a lot. This here is a front loader on a tractor frame, which you see the lifetime part, which is affected during the kind of working. We do simulation here with tractors maneuvering. So a lot of things what we're doing in simulation. Here you see a tractor on some kind of a bumpy field, because the tractor is different to a car or to a truck. A tractor is driving everywhere where a truck and a car will not drive. This is a big challenge, and we do a lot of simulation. But where we do spend a lot of money too, you will see now. You see the first picture which I have shown on the simulation side. We do also kind of physical testing here with several hydraulic tests. Here, this is a special device where we do some kind of moving. Here there's a drivetrain. It's a big gearbox with a lot of gears in, maybe 30, 40 gears. They are in oil, and here what you simulate, it can turn around and you can shift up and down. You simulate here with testing when the tractor is driving on a side hill, maybe in the Alps or in the mountains, or mowing in the States on the highways, maybe for a whole day, side leveling, which is not nice to the oil in a transmission, because some gears do not get enough oil, so you have to simulate some kind of oil, I would say, oil placement in a gearbox, and all the things which are going in the gearbox during driving. Here another item. Just go back. Another item here. So our tractors are running not in the Antarctic, but near. They're working in northern Canada, which you get up to minus 40 C in the winter time. You also get 50 C in Arizona during the summertime. So what you have here, we do cooling tests in such kind of chambers for starting, for how the hydraulic system is working when you get up to minus 40 C. All the valves and so on are working. And in the summertime, we also can get here up to 50 C temperature and humidity of 100%. So we do a lot of testing here. Another item here is, this is named a 7-poster. What you do here, you engage a tractor on 4 posters here, which are I would say, simulating or reproducing loads where the tractor is driving to an uneven field or on an uneven road. And other side, what you do is you have other 3 cylinders here who give you the reaction forces on the sides. And in addition, the engine is running, and the engine is not running on low idle without supplying no power. It's also broken with a brake in the back, which you can load the engine sequentially on high load, even load, or something else to get the temperature and other things, I would say, on this test stand. Here, another item which is also from the simulation side, I will come later to it, not so easy, electromagnetic compatibility. This is very, very important. A tractor has 25 controllers in the tractor itself, and if the controllers are affected by maybe a mobile phone amplifier or other things, and the reaction of the tractor is maybe the lights are not working or other systems are not working because everything is controlled by software and by electronics, you will have a problem, and you have to show also some officials that this thing is working. This is very important, that you see what the tractor emits and what kind of effect it has when some kind of outside radiation comes in. And for a lifetime, we do also some kind here of robot testing. What you do is you slam the door maybe 10, 20, 50,000 times. This is what the guy is doing. He's jumping in and slamming the door, that it's closing, and you have here glass, you have here some ceilings out of rubber and other things, which will give you some kind of problems when you try to simulate. So we do a lot of experimental testing, and we do a lot of simulation. But what we want to try to do is we want to simulate reality. With simulation, what you do is you create models, which you say models for reality, but also in the experiment you do some kind of a simulation. You try to simulate reality. Numerical simulation, clear. You do the models. You can do it without some kind of hardware. This is the very good stuff with numerical simulation. You can try out ideas, you can try out things before you start to invest money in physical models. And on the other side, on the experimental simulation, you try to, I would say, want to get a little bit more close to reality and also include things which you are not able to do with your normal simulation tools. But for the numerical simulation without of a check with reality or with experiments, it's, I would say, very risky. You need some kind of, I would say, a check in the early phase. So what you do is you have an idea, you find out some kind of new things, new ideas. The designer is the guy who creates new ideas, and together with the guy who is doing the simulation, you can build up a physical model, try out if the physical model behaves what the designer thinks, and then you need some kind maybe of feeding experiments to do better, to know you're going on the right way to the future. And when you see the development phase in every kind of product, you see here where you use the numerical simulation and where you use the experimental simulation. Competitors, what do you think? 2040, it's not far away. Is this a test lab? Do we need a test lab anymore? Or do we get rid of all the people in a simulation office because testing took over the simulation part? Everybody is laughing, so I can agree, but both elements, the test lab and the numerical simulation office with the people in, I would say, will exist also in 2040. Some people are dreaming that in 2040 or 50 you can do everything with numerical simulation. I think there's a dream, but you can do a lot more and you can do a lot better if you do it right. So, are numerical simulation and testing simulation partners? I will show you some elements which you say when you do numerical simulation. If the confidence in the numerical simulation is sufficient, what means confidence? You know what you do by experience, and experience also you have compared it with testing results or with results out, I would say, of the community of your users who are using the products which you defined. Confidence in numerical simulation is insufficient, but at least as high as in experimental simulation. So not every time you know that your simulation is quite, I would say, a picture of the reality, but it looks like that it's as good as when you do some kind of a testing, but for the testing you need a physical model. A physical model is expensive, and with the numerical simulation you can do much better because your model costs you manpower, yes, time, but you can do a lot of changes to the model and not to a physical model. Hardware not yet available. This is a very important part. Most of the time, when people say we need a test, people go back and say, oh, maybe we do it better in the numerical simulation because hardware is not yet available. And this is a very important part. When you look in the development office, you start to order parts, and parts are not ready in time, and so they say, okay, better numerical simulation helps you anyway, and later we can do the testing. Hardware prototypes too expensive. Sure. When you have an idea and you have to invest $1 million for a prototype, you can go to your boss and ask, and he will ask you 20 questions to, I would say, find a better way to do things, I would say, earlier in another phase to get a confidence level that when you start to invest in hardware, that you're on the right way. Physical test bench not available or too expensive, the same. The test probe or the test object is one item. Your test environment must be there. We have seen that the test environment for this, on the first presentation, when you want to go to Mars and to do things, you look to the test environment, what they had to find out of this one biological reactor is working. It's a big thing. You cannot do it from today to tomorrow. You have to invest long term to I would say, to be able to do it with physical tests, I would say, laterwards. Physical iterations too time consuming. No results available before order date for next hardware build. With numerical simulation, you can do a lot of things very fast. The computers are fast. You can change your ideas. You can change loadings. You can change a lot of things on the fly, I would say, and to ask your model what is the reaction. So what you do is like a doctor. You go to a doctor and you are the guy who's doing the simulation. You have your model. This is the person, and you ask the person about in which way he reacts to some kind of outside influences. So what you do is you apply new conditions, boundary conditions, and other things, and you see how your model will react. And the good thing is, the doctor normally he can do the same, but he asks you, maybe he's measuring your temperature and so on, but he is not able to easily, I would say, to go inside or to see what's going on inside, because then he has to use a knife or some kind of other things to go more in depth in to see what's going inside. With the numerical simulation, you are able to, I would say, to analyze in depth what's going on inside your structure, your design, your model. This is very helpful. Testing of physical phenomena is technically not possible or only with unacceptable high effort. Some things you cannot test so easily, because testing also maybe reflects the results. When you have some kind of very nice microstructure, you want to find out results and you want to get some kind of readings from it. We find out that sometimes your measuring equipment has a high influence, for example, on the results. So how to say results are okay without the measuring equipment and with the measuring equipment. So simulation here is one of the items to use. Effort of optimization or sensitivity study too high for physical tests. This is the playground for simulation. Here you can do a lot of sensitivity studies, and I will show you how to do it at best in a sequence. Because here you do not need 20 different type of hardware parts which have this or this changes included. Here you can do it on the fly. You as a guy who's doing the simulation, you can speak with the designer who is the creator of an more or less of a product, and can ask him, what do you think about this or this direction, and you can help him because you are the doctor. You can tell him what is best for the patient. The patient is the design, and what is not helping. And so you can create together with the designers, I would say, a better product. Health risk for machine operator too high during experimental testing. For example, we as John Deere producing tractors and other equipment, and this equipment do not only operate in flat ground. We operate in mountains, on side hills, and when you look sometimes, when you go to the Alps and see how these guys are mowing and so on side slopes, and you are on a tractor by yourself, and I have done it, you do not like it, because these are experts and they do high-risk things. And sometimes they overstretch physical limits. Physical limits means the tractor is rolling sideways down and stopping somewhere. And we also have to find out if the structure, the cab structure, is sufficient to support the guy in a certain room inside, that he is not hurt by running. I would say that the cab is, or the engine is going in the cab. So normally we do not do this rollover test because it's, I would say, too risky for the people. So we do it in different ways. We do simulation. We do also some kind of other testing. But simulation, we do a lot of things also to prevent, I would say, health risk tests. On the other side, why we do experimental simulation? I tell you, I'm now retired, and the last thing what I have done in my last 3 days was inauguration of a new testing building for 11 million euros. 11 million euros, you can hire a lot of people to do simulation, right? We had also a lot of people who are doing simulation. But there is a need for experimental simulation or experimental tests. So companies, also the automotive companies, never will get a car in production before they have sent out 50 or 100 examples, more or less, going outside in different areas in the world, and to get more information in what the customer is doing and what kind of, I would say, boundary conditions they are missed during simulation. Confidence level in numerical simulation is insufficient. A lot of tests where you do maybe a friction-related things in transmissions, for example, where you look for the oil placement on gears and so on and so on. It's very complicated, and the trust in the numerical simulation is, I would say, on low level. Confidence level in experimental simulation is sufficient. Also, you do something here because you have history of things, and you will find out that in your real testing of real hardware, you will find out things which you were not able to integrate in your numerical simulation, some kind of boundary conditions, which you integrated in your physical tests, which are not visible to you during your simulation. Confirmation tests, sure. You need this kind of tests to confirm the previous numerical simulation with insufficient confidence level. So this is, what you do is here, you do something here in experimental testing to compare it with what you have done with your numerical stuff, and you get better with the comparison with your numerical simulation over time. Correlation tests. This is clear. Correlation test is something which you do to correlate your numerical models to your physical models, and to find out what you miss on one side or what you can do on the other side. Compute power for numerical simulation not available, or the numerical simulation models too slow. Okay. When we come to other things, you see, you can do a lot of experimental simulations, and a lot of items is experimental simulation and other things are partners. You have to do it right. You have to do it in the early phase. You see only one item here. You have to start early with your simulation tools, and then you are, I would say, on the right path. The conclusion is the numerical simulation and experimental testing are partners, but there's a need for both. This is clear. But use the right tools at the right time during development. The numerical things you have to use upfront in your, I would say, pre-definition of new items. We say technology development programs. You have to do numerical simulation. Before you have hardware, you do the numerical simulation. And the experimental stuff you do laterwards when you have the optimized designs. And the synergy will increase your productivity and speed up your development time if you do it right. Place your simulation, I would say, methods early in your development phase, as early as possible, to prove out ideas that you get in with the testing to get a higher confidence, but on optimized design. And if you do it right and you compare it, you get the best, I would say, from both worlds. And one item which says that John Deere makes a footpath in the ground, and with methods from yesterday, you develop products from yesterday. So with the combination of simulation and testing, doing right in the sequence, you will get the best products in the world.